One common form of integrals that shows up in lots of applications, in physics especially, um, involves a lot of trigonometric functions. And these basically show up a lot in situations that involve geometries that have some sort of circle involved, so spherical geometry or cylindrical geometry, things related to point charges, things related to gravity. Um, so there's a bunch of situations, and trigonometric integrals arise in these situations, and I'm going to go through some approaches to solving these trigonometric integrals. So let me just write that down, though, that trig integrals show up a lot in physics, and especially when we're dealing with any sort of circular geometry. Okay, so there's a couple of common approaches to deal with these problems. So we'll have basically at the end of the day, kind of three tools at our disposal for dealing with these types of integrals. And what I'm going to do is basically just run through a bunch of examples, and then hopefully after we go through those examples, the different approaches that we've taken will become kind of clear, and we can kind of come back and summarize what those approaches are. So one of them shows up in situations like this one. If I am trying to compute the integral of, say, sine squared of x dx, we know how to take the integral of sine, but the fact that we're squaring it makes it a problem that we don't know how to deal with anymore. To deal with this, what we're going to do is use a power reduction formula. So this means we're going to start having to rely on some of our trigonometric identities that probably many of you have long forgotten. So hopefully by the end of this, we'll have highlighted the few identities that you really do need to relearn and have in your back pocket for these. So in this case, power reduction. Power reduction is one of the most important ones that we're going to need. Power reduction formula states that sine squared of x can be rewritten as the following. It can be 1 minus the cosine of 2x over 2. And similarly, if I'm dealing with cosine squared, that one can be written as 1 plus the cosine of 2x over 2. So these are the two power reduction formulas, and in this case, obviously, it's the one on the left that we're going to be using. So I can rewrite the integral as the following. We've got the integral of the sine squared of x dx, and I can rewrite that as the integral of 1 minus cosine of 2x whole thing over 2. And to make life a little bit easier, instead of writing it this way, I'm going to split that single fraction up into two separate fractions and just write it as a half minus cosine of 2x over 2. Right? These two forms are equivalent. And let me just toss in my parentheses for good measure. So this is what we wind up integrating. And it breaks into two separate integrals. We can integrate the 1/2, which is easy. And then the other one is this cosine of 2x, and we can integrate that one using a U substitution. So we're going to break this into two separate integrals. The first one is the integral of 1/2 dx. And then the second one is going to be minus the integral of cosine of 2x over 2 dx. And for the second one, I want to use a U substitution. So I want to let U be equal to 2x, this piece that's inside of here. The derivative is going to be, so when we get du, that's going to be 2 dx. And I can basically go in and substitute through here. We can basically recognize that I just need an extra factor of 2 out here, and I can write this whole thing in terms of u. So again, the first integral I'm not touching, but the second integral, the idea is I'm going to rewrite this as a cosine of 2x, and I want a 2 dx. I have it written over 2. Here's my integral. I've added in this factor of 2 here in essentially the numerator. I need to account for that by adding another factor of a half somewhere. So I can do that by just doing another 2 down in the denominator here. So I'm both multiplying by 2 and dividing by 2, but now I have this 2 dx, which is exactly what I need to write this as du. And that means this second integral gets rewritten as minus the integral of cosine of u, right? Cosine of 2x. 2x is what we said would be called u. I've got my 2 dx, so I've got my du, and the denominator is now just a 4. So here's the integral that we're looking at, and I can do both of these integrals quite easily now. The first integral, when I do the integral of a half, it's going to be 1/2 x. For the second integral, I'm going to have basically a factor of 1/4 pulled out in front of everything, so I'm going to move this 4 in the denominator outside of the integral, and now we're just integrating cosine. What's the integral of cosine? It is sine. And we've got our plus c, and I can't forget though that right now I have it mixed. I have part of my answer written in terms of x and part of it still written in terms of u. U was something we introduced. The original problem was entirely in terms of x, so we need to remember to come back and convert everything to be back in terms of x again. And so I need to replace this u back with the 2x that we started with. And so this final answer in this case is 1/2 x minus 1/4 sine of 2x plus c. So there is our answer for that problem. So power reduction formula is going to be one technique that we're going to use a lot. Typically, the most common place to use it is when we're dealing with even powers of a single trig function. So like sine squared, sine to the 4th, cosine squared, cosine to the 4th, go all the way up to 6th power, 8th power, and so on. You're going to be using power reduction formula in any of those where you're just dealing with a single trig function raised to an even power. The next approach I want to look at is going to be for a problem that might look like this. So the integral of sine cubed of x dx. So notice in this case, it's similar to the problem that we had, but now the power is odd instead of even. Whenever we're dealing with odd powers, what we're typically going to want to do is use a Pythagorean identity. So in this case, we'll use a Pythagorean identity. This is hopefully one that you do remember. The most common one is sine squared of x plus cosine squared of x equals 1. There's a similar formula involving tangent and secant and cotangent and cosecant that you can get by just dividing this whole equation either by sine squared or by cosine squared, and you can derive the other versions of the Pythagorean identity. But the idea is, in this case, what I want to do is split this sine cubed up into a sine squared and a sine. So, and we're going to use that along with this identity right here. So we note that sine cubed of x is equal to sine squared of x times another sine of x. And this sine squared, I'm going to replace using this Pythagorean identity. So I'm going to use the Pythagorean identity to solve for sine squared and see that sine squared of x is equal to, if if I isolate this piece of the equation, I can do that by just subtracting cosine squared from both sides, and I'll get 1 minus cosine squared of x. So I can get this whole thing to be rewritten as 1 minus the cosine squared of x times the sine of x. Okay, why does this help us? Well, this is going to help us shortly because we're going to be doing basically an integration by parts in some cases, depending on the problem, or in this case, we'll still be able to get away with a U substitution. Remember, the idea is I'm looking for a part of the function. When we're doing U substitution, we look for something that looks like a function and something that looks like the derivative of that function. And I've got a cosine and a sine, and I know they're related as derivatives, so I'm going to be able to do a U substitution on this piece to simplify things. So let's see exactly how that pans out. But again, that's our clue. By splitting this up into pieces that involve sine and pieces that involve cosine, and once I've got both, then I have a function and its derivative, and I can use that, exploit that to do a U substitution. So in this case, we get that our integral of the sine cubed of x dx can be rewritten as the integral of 1 minus cosine squared of x times the sine of x dx. And here's where we're going to do, oops, let me zoom out a little bit here. Sorry, dx. Here's where we're going to do our U substitution. So I'm going to let U, in this case, just be the cosine of x. And that means that du, the derivative of cosine is going to be negative sine of x dx. And so we can use this to now rewrite this whole equation that we've got here in terms of U. And we can actually do it in a couple of steps. I'm going to break it up into two pieces. You can think of it as basically we're just going to be distributing the sine function through. So one of the two integrals that I'm going to be dealing with is just going to be sine of x dx when I distribute the sine of x through to the 1. And the other one will be the minus integral of cosine squared of x times the sine of x dx. And this is the one that I will use the U substitution that we just came up with right here. So I'm not going to touch the first one for now, but the second integral I want to rewrite. You can think of basically this whole piece is being made up of this piece and the negative sign that we've accounted for, right? We can change that negative sign and account for that negative sign there. Or alternatively, we could sort of force the negative sign in here and then account for that by multiplying by yet another negative sign out here, which would flip this sign back to positive. So however you want to think about it, maybe we want to write it as plus the integral of cosine squared of x times negative sine of x dx. So maybe that's a clear way to do it. I've moved the negative sign from the outside in here, and now I have exactly what my du looks like. And what is this piece, cosine squared? Well, that's just u squared. And my integral becomes the following. So again, I'm not touching the first one yet. We're just going to have the integral of u squared du. There's our substitution. So now let's actually evaluate these integrals. The integral of sine is going to involve cosine, and we just need to remember, does it have a negative sign or not? I know the derivative of sine is cosine, but the derivative of cosine is negative sine, so I need to take that negative into account and put a negative there. So that's the integral of the first part. For the second one, what is the integral of u squared? Well, that's going to be 1/3 u cubed, and I've got to remember my plus c. And again, right now, I have the whole thing written partially in terms of x, partially in terms of u, but the original function that we're trying to, or the original equation that we're trying to integrate, or function rather, that we're trying to integrate, is written entirely in terms of x, so I need to convert this u to be back in terms of x. And so we'll do that as our final step and write that this 1/3 of u, recall that u was just cosine of x, this is cosine cubed of x plus c. There's our final answer for that problem. So, looking at these two approaches, the gist of the idea is, again, if we're dealing with a single trig function and it has an even power, we're going to use power reduction on it. If it has an odd power, we're going to use this Pythagorean identity to split it up so that we get basically both a function and the derivatives of that function. Here it was in terms of sines and cosines. If we're dealing with tangents, or secants, we'll try to split it up to be in terms of both tangents and secants. And similarly with cotangents and cosecants. Those kind of go in pairs together. So we can deal with problems in a number of ways. I want to just go through and do a bunch more examples. So let's do another example. Let's say we had, this won't be too bad, sine squared of x, cosine of x dx, and we're integrating that. Well, this one's easy because it involves a combination that already has both sines and cosines inside of it. We've already got everything we need to do our U substitution. I've got a function, and I've got the derivative of that function. So here's some function that's then being squared, and here's the derivative of that function. So I identify immediately that I'm going to let u be equal to the sine of x. That means that du is going to be the cosine of x dx, and I've already got my whole du sitting right here, and I can rewrite this whole thing as just the integral of u squared du. And doing that integration, I'm going to get 1/3 u cubed plus c, and then convert back to the original function to get 1/3 sine cubed of x plus c. So they go fairly quickly once you get the hang of it down and you recognize that it's U substitutions more often than not that we're looking for here. Let's do another one. What would I do if I had the same problem but simply a sine cubed of x, cosine of x dx? So think about this one for a minute. How would this one differ from the one that we just did up here? The answer is it basically wouldn't. We're going to do the exact same U substitution. The only difference is instead of winding up having to integrate U squared, in this case we're going to integrate U cubed, and we'll wind up with 1/4 sine to the 4th of x. So let's see that. I'll let U be equal to the exact same thing. Du is going to be the same thing as the previous problem. And this is now just the integral of U cubed du, right? Again, here's my du. Oops. Sitting right there. And this is simply U cubed. And we integrate that, get 1/4 u to the 4th plus c, convert back to x. I've got 1/4 sine to the 4th of x plus c. Okay, so those aren't too bad. It's nice if we have a trig function and its derivative showing up with just a first power. But what if we had something a little bit trickier, like this? What if instead of the problem we just did, what if I was trying to find the integral of sine cubed of x times cosine squared of x dx? Well, this makes things a little bit trickier. We've got still some pieces that involve sine, some pieces that involve cosine. I clearly have some functions and the derivatives, but I don't have them totally clear which is going to be which. And the goal in this case is going to be to pull out basically one one function that we want to deal with. So either pull out one cosine or pull out one sine. And in this case, I'm going to pull out one sine of x from this. And hopefully we'll see that why I want to do that in just a minute. You could also do this by pulling out one cosine of x. And we could ultimately get the same result. But let's just go through it. Let me show you how to do this problem. And then we'll kind of think about why we made the decisions we made as we did this. So what I want to do is basically pull out one sine of x from this. So I want to rewrite this as the integral of, in this case, sine squared of x, cosine squared of x, and here's the sine that I pull out, sine of x dx. So I pulled out a sine of x, and that reduced the power over here from being a cube to a squared. So here's squared times the other sine x gives me back the cube that we would have. So by writing the equation this way, I've basically picked this piece to be the thing that I want to force to be a du. And alternatively, we could have tried to pull out a cosine. That might have made things a little bit trickier. We'll look at that in just a minute, but in this case, we pulled out one sine of x. I want to force this to be the du, and if this is the du, what does that mean the u must be? U must be equal to something that involves a cosine of x, right? So if u is just cosine of x, the derivative of cosine is negative sine. I don't have that negative symbol here. So if we want to put it here, we can either force it here or we could put a negative sign here. I don't want to put a negative sign in my u. What I want to do is basically, I'm going to force a negative sign here and then account for that by putting another negative sign out in front of everything. Okay, so although again, you could have a negative sign here, I just don't want to try to remember dragging that negative sign around later on in the problem. I want to deal with the negative sign right now. So I snuck a negative sign in right here and accounted for it by pulling a negative sign out here. And now I've taken care of the negative sign. I don't need to worry about it later in the problem. Okay. I need to now write the rest of this problem in terms of u. So this is going to be the general approach for a problem that looks like this. If we've got a mix of higher powers of both sine and cosine, pick basically something where we can pull out a trig function, like to the first power of one of these two things. In this case, I wanted to pull out sine because it's going to make my life easier. Because when I pull out sine, it leaves me with an even power of sine in this part. And even powers of sine are going to be very easy to convert into cosines. So I've broken it down. I've got a du. And now I need to force everything over here to be written in terms of u, which means I need to make everything be written in terms of cosine. Part of it already is written in terms of cosine. Part of it is not. So I need to reconvert this to be written in terms of cosine. So how do I use that? Or how do I do that, rather? I need to use the identities that we talked about earlier, either the power reduction or in this case, because it's nice, easy square power here, I can use the Pythagorean identity that says that sine squared of x is the same as 1 minus cosine squared of x. Now I have my cosine squared of x, and I have my negative sine of x dx. If you want to think about all of these pieces written out separately. So this whole thing is now in terms of u. And this whole thing is my du. And we have essentially another U substitution problem. We just had to be clever about the way that we picked this apart. And so again, I'll come back and we'll talk about this as we do more examples. Once you do a few of these, you kind of start to see the pattern and it becomes easier to anticipate what piece you should pull out, how you should break things up. So I'm going to rewrite this whole thing as my negative integral of recalling that u is equal to cosine of x, this is just 1 minus u squared, and this is u squared. So I have 1 minus u squared times u squared times du. For this part, I can just distribute through, and I can rewrite this as negative the integral of u squared minus u to the 4th du. We can integrate that in a pretty straightforward way. I'm going to get negative 1/3 u cubed. The negative sign will distribute through and make the second term a positive, so plus 1/5 u to the 5th plus c. And the last step is to convert back to the original function that involved x. So I'm going to replace my u's back with cosine of x's. We get negative 1/3 cosine cubed of x plus 1/5 cosine to the 5th of x plus c. Okay. So hopefully as you went through these first two seem pretty obvious. It's very obvious that we've got a function and the derivative of that function, and it's easy to split up because the cosine is already to the first power. In this one, we have a function and we have its derivative, but we also have another function and its derivative. And how do we pick which one is going to be the function that we're going to use and which one is going to be the derivative that we're going to use? Well, what we need to keep in mind is once we pick which one's going to be the function and which one's going to be the derivative of that function, once we make the derivative of that function, everything else has to be written in terms of the original function. So I know this is confusing. I'm saying a lot of words, and I can even hear myself speaking and realize how confusing that sounds. But as we go through this example, let's just reconsider. I pulled out a sine instead of a cosine here. I pulled out 1 sine of x, and I chose to make that one that's to the first power, that needs to be the piece that is our du. So whatever piece we pull out and make it to the first power, just like in these two problems up here, the one that was to the first power, that winds up being our du term. So same thing here. I picked one of these to pull out, make it to the first power, so that I had a du term. And in this case, I picked that sine of x to pull out. And that was really convenient because it left me with an even power of sine. In fact, it left me with sine squared. And I have a very easy way to convert from sine to cosine if I have an even power like this, because I can just use that Pythagorean identity that we used right here. So that's going to be kind of our goal. If we can pull one out that leaves us with basically both these other terms being squared, that's great, because now it's really easy to write these entirely in terms of cosine. Hopefully that kind of makes sense. So let's maybe do another example and see what the approach would be for this one. So let's do another example. And maybe this will be more clear once we do a second example. So I want the integral of sine squared of x cosine to the 5th of x dx. Okay. So which one should I pull out? I know that I need to pull out, I see a function, I see its derivative, I see a function, I see its derivative. Which one's going to be the function? Which one's going to be the derivative? If I were to pull out a sine of x, that would mean that whatever's left over needs to be written in terms of cosine. And that would leave me with 1 sine of x and a cosine to the 5th of x. The cosine to the 5th is great, it's already in terms of cosine. So if I pulled out, if we pull out a sine of x, which I'm going to force to be the du term, so it would be the sine of x dx rather. If I force that to be the derivative, that means that everything else would need to be written in terms of cosine. But what would that leave me with over here? That would leave me with a sine to the first power times a cosine to the 5th of x times our sine of x dx. And this part is the easy part. Sorry, let's write my integral. It's already in terms of cosine, which is great, but now I need to write this in terms of cosine somehow. And without it being squared, this is not an easy thing to convert back to cosine. I have to do a bunch of ugly tricks to kind of either shift this or do some weird other ugly things. So this makes it actually a little bit harder. The point is, I do not want to pull out a sine of x in this case. In this case, it would be better to pull out a cosine of x. And so let's do that instead. So I don't want to pull out this. That was a bad approach. Let's pull out instead a single cosine of x. And that's a little bit better because that will leave me with a sine squared of x, a cosine to the fourth of x, and a cosine of x dx. And now I have my du, which tells me if this is my du, then u is going to involve the sine function. In this case, it'll just be sine, and I need to write everything over here in terms of sine. This part is easy, it's already in terms of sine, and this part isn't that bad either because it's an even power, and I can use my Pythagorean identities to easily rewrite this in terms of sine. So that's going to be the idea. So if this is my du, then what that implies is that we are letting u be equal to the sine of x. And so that my du winds up being the one that we just picked. Du would be cosine of x dx. Right? The derivative of sine is cosine. I don't even need to worry about negative signs in this case. We're good as far as negative signs are concerned. So part of this function is already easy to write in terms of u, and the other part isn't going to be too bad either. How do I rewrite this piece? Well, we'll use that we'll use that Pythagorean identity again to rewrite this as sine squared of x, and that cosine to the fourth, I'm going to think of it as cosine squared of x squared times my cosine of x dx, which allows me to then write sine squared of x inside parentheses. I'm going to use my Pythagorean identity. Cosine squared is the same as 1 minus sine squared, and then the whole thing's just being squared. So now this whole thing is written in terms of sine of x, which is our value, our substitution we made for u. So I can write all of this in terms of u, and here's my du sitting right there. So when we do that substitution, I have u squared, I have 1 minus u squared, quantity squared, and then I have du. All we need to do over here now is basically FOIL this out, distribute this through, and we'll have a big, ugly, but just a polynomial to integrate. So this is going to be the integral of u squared. When we FOIL this out, I'll get 1 minus 2u squared plus u to the fourth du. Then we'll distribute that u squared through. We'll get u squared minus 2u to the fourth plus u to the sixth times du. So all I've done is distribute this u squared through to these three terms to get this. And now I simply have a polynomial to integrate. And it's going to be 1/3 of u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh plus c. And our last step is to rewrite this whole thing back in terms of the original variable x instead of u. And we do that by simply going back and replacing all the u's with sine of x's. So this is going to be 1/3 sine cubed of x minus 2/5 sine to the fifth of x plus 1/7 sine to the seventh of x plus c. There's our final answer for this one. Okay, so hopefully that makes some sense. Again, we're always going to have to pull out a single power, so a single power of either our sine or our cosine, and try to do so in such a way that it leaves even powers of the remaining pieces. And even powers are really nice because they allow us to utilize the Pythagorean identity. Okay. What if we have one that involves, instead of sines and cosines, what if we've got one that involves tangents and secants? Okay. So if we're dealing with tangents and secants, we need to remember what the derivatives are. So recall that the derivative of tangent, so if I take the derivative of tangent of x, the derivative of tangent is secant squared of x. And if I take the derivative of secant of x, recall that its derivative is secant x tangent x. So for problems that involve tangents and secants, these are the du's, the du terms that we should be looking for. We'll also use, along with this, the tangent and secant version of the Pythagorean identity, which is that basically if we, let's just do it real quickly. So if you can't remember this, this is the easiest way to do it. Just start with the one you can remember. Sine squared plus cos, where's my undo button? There we go. Sine squared plus cosine squared equals 1, but I want to now rewrite these in terms of tangents and secants. So how are we going to do that? Well, to get this to change from a sine to basically we've got to look at which terms, if we divide this whole thing by sine squared or whole thing with cosine squared, are we going to wind up with tangents and secants or cotangents and cosecants? So in this case, if I were to divide everything by sine squared, this term would become 1. But over here I'd have cosine over sine. That's a cotangent, and that's not what I want here. So instead, I'm going to go through and divide everything here by cosine squared of x. Cosine squared of x. Cosine squared of x. And now I have sine squared over cosine squared. That is tangent squared of x. The cosine squared over itself is plus 1, and that's equal to 1 over cosine squared. That is secant squared. So here is the Pythagorean identity involving tangent and secant. So this is the other piece that we're going to use. Again, it involves even powers of tangent and secant. So that's what we're going to be going for. So let's look at an actual example and see if we can put this to use. So in this example, if I can leave some of these up here, I want the integral of, let's say, secant cubed of x, tangent cubed of x, dx. What should we pick? And just let me tell you, sometimes these are going to work out such that it'll work out nicely either way that you pick it. And sometimes it'll work out only nice if you pick it one way. And sometimes there are a few problems that really are hard to make them work out nice pretty much no matter what. But let's go through this one and kind of just trial and error our way through this one, see what works and what doesn't work, what makes things easier, what makes things harder. And hopefully we can use that to kind of develop some rules about how to deal with these secant and tangent problems. So our goal in this case is to try to get these types of pieces. These are the important things that we care about. This, oops, let's do it in a different color. So these, and hopefully that'll leave us with some other even powers that look like these. Okay, so our goal is to pick du's, pull out either a secant squared or a secant x tangent x that will hopefully leave us with even powers of secant and tangent so that we can utilize this, right? This involves even powers. Our hope is once we've picked our du and pulled that out, that we're left with tangents and or secants that are even powers so we can utilize this formula. So if I were to pull out a secant squared, if I pulled out a secant squared, what would that leave me with here? So if my secant squared dx was pulled out as my du, it would leave me with a secant to the first power and a tangent cubed. That is not necessarily ideal because it isn't even powers. It's leaving me an odd power secant to the first power of both the secant term and tangent cubed, also an odd power there. So that's not going to be the thing that we want to pull out. I don't want to pull out a secant squared. Instead, I want to pull out a secant x tangent x, because if I pull that out, it reduces this power down by 1 to secant squared. It reduces this power down by 1 to tangent squared. And now I have both secant squared and tangent squared. They're both even powers, and I'm going to be able to use this. Hopefully that makes sense. So pull out, for our du, I'm going to pull out a secant x tangent x, and the dx in a sense. So pull that thing out and call it du. And we will rewrite this as secant squared of x tangent squared of x times secant x tangent x dx. Right? Here's our du. What does that mean our u looks like? So that must mean that our u is secant of x. So if u is secant of x, that gives us this particular du, and that means I want to write everything over here in terms of u, in terms of secant of x. This part is good, but this tangent squared I need to rewrite in terms of secant. And luckily, I have excuse me, I have a way of doing that right here. So we want to write all of this in terms of u. And for us, that u is secant of x. And so what we get out of this is that my secant squared term is going to stick around, but tangent squared, I'm going to come back up and use the Pythagorean identity to isolate the tangent squared. So to get the tangent squared by itself, I would have to subtract 1 from both sides of this, and I'd be left with secant squared of x minus 1. So that is the tangent squared term. And now I have secant x tangent x dx. And I have everything in terms of u and du, and we can now write it in terms of that. So we've got a u squared minus 1, and a du. Just to be totally clear, here's how those pieces all match up. Hopefully that's clear. Okay. To do this integration, we just distribute through. I'm going to have a u to the 4th minus u squared du. Do that integration. We'll get 1/5 u to the 5th minus 1/3 u cubed plus c. And then all I need to do is go back and substitute back in for the original variable, which is x, using our substitution right here. So replace those u's with secants, and we will get 1/5 secant to the 5th of x minus 1/3 secant cubed of x plus c. And there is our answer. So again, this was the thing that was better to pull out, secant x tangent x. This was the better du to pull out because it left us with even powers of both secant and tangent, which are much easier to switch into the other. So if we wanted to switch everything into secants, that's easy, as we did here. Or if we had wanted to switch everything into tangents, that would have been easy as well. But in this case, there is no reason to switch things into tangents because this is our u. If this is the du we pick, we want to write everything in terms of secants here. If we'd pulled out a secant squared, we would want to write everything else in terms of tangent. And we would have, again, wanted everything to be left with even powers. Okay, let's try yet another one. So in this one, Let's do a definite integral, just because we haven't done any of those in a while. So I want to do the integral from 0 to pi over 4 of, let's say, secant to the fourth of x, tangent to the fourth of x, dx. So again, we need to figure out what we're going to pull out from here in order to leave behind preferably even powers of both functions. And I can either pull out a secant squared or a secant tangent. In this case, if I pulled out the secant tangent from my du, it would leave me with odd powers, and so I don't want to do that. Instead, I want to pull out the secant squared. So I want to pull out secant squared of x dx. That'll allow me to write this as the integral from 0 to pi over 4 of secant squared of x, tangent to the fourth of x, times our other secant squared of x dx. So here is my du. If the du is secant squared, that must mean that what did we let our u be? Our u must have been tangent, because the derivative of tangent is secant squared. So this is the idea. Here is our u. That must be our du. And that means I want to write everything in terms of tangent of x. So this part is fine, it's ready to go. I just need to rewrite this part. So that will be our goal. I want to rewrite this as the integral from 0 to pi over 4. The secant squared term, if we go back up to our, here we go, to our Pythagorean identity, secant squared I can rewrite as tangent squared of x plus 1. So I'm going to rewrite this as tangent squared of x plus 1 times tangent to the fourth of x times our secant squared of x dx term. Now we can convert everything to u's, and that means that once we convert this to u, we'll have the integral of, this is going to be a u squared plus 1 times u to the fourth and du. But we also need to now convert our bounds of integration. Alternatively, we could leave them in terms of the x variable. I'd want to make that explicit. I could write x equals 0 to x equals pi over 4. And remember that after I integrate these, I'll need to convert back to x and then plug in these bounds. Alternatively, we can just switch those bounds now, and usually that's what I wind up doing, but it kind of depends. So I want to switch those bounds to be in terms of u. Let's just do that right here. If I go back up to my substitution, which we've got written right here, what do I get for u when we plug in our lower bound of 0 for x? So the tangent of 0. If you don't remember what the tangent function looks like, that's fine. But luckily, we can just rewrite it hopefully in terms of sines and cosines and use that to kind of jog our memory. So this is the same as sine of 0 over cosine of 0. Hopefully that jogs your memory. The sine of 0 is 0, the cosine of 0 is 1, and this whole thing is 0. So turns out x equals 0 corresponds to u equals 0 as well. And at pi over 4, so for the upper bound, when I plug in pi over 4, so just to be clear, this is a u, kind of looked like an n the way I had it written. There we go. When we do pi over 4, that's going to be the sine of pi over 4 over the cosine of pi over 4. Hopefully you remember your unit circle a little bit. Pi over 4, 45-degree angle, is where both the x and y coordinates, which correspond to cosine and sine respectively, are the same. And we wind up with, it turns out this is root 2 over 2 divided by root 2 over 2. Anything divided by itself is 1. And so we're going up to an upper bound of u equals 1. So there's what we need to integrate. I can distribute through. We'll get u to the 6th plus u to the 4th du. We're integrating that between 0 and 1. We will get 1/7 u to the 7th plus 1/5 u to the 5th. And that's going to be evaluated between 0 and 1. The lower bound, when we plug in 0, it's not going to contribute anything. Both of these will disappear. They'll become 0. And only the other upper bound will contribute, so it's just going to be 1/7 plus 1/5. And if you want to write that as with a common denominator, the common denominator would be 35. So 1/7 is 5/35. I'd multiply the top and bottom of this by 5, top and bottom of this by 7, plus 7/35, and we get 12/35 as our final answer. So there's the answer for that one. Let's do maybe like 2 more of these. Just as a heads up, I'm not in these examples going to do any cotangent cosecant problems. You would do them the exact same way, but I will also not give you any of those on any exams or quizzes. So just keep that in mind. I think you may have 1 or 2 in the homework, but I won't give you those on an exam. Just in the interest of time, we'll stick to either sines and cosines or tangents and secants. And if you want to do one with cotangents and cosecants, it's the exact same thing. It's just more trig identities to remember, and I don't want that to be the emphasis here. So let's try a couple more problems that involve just tangent and secant. These ones are actually surprisingly kind of tricky, so let's do this one. What is the integral of tangent cubed of x dx? How do we do tangent cubed of x dx? Well, in this case, there isn't any of, sorry, going way back up here. Neither of these du's are possible to pull out because there is no secant that shows up anywhere. So this approach isn't going to work for this problem, right? There is no secants in tangent cubed, so I don't have either of these du's. What we're going to have to do instead is start with a Pythagorean identity to see if we can split this up into something that involves both tangents and some secants. So we're going to basically force this thing that right now only involves tangent to involve both tangent and secant. So I'm going to rewrite this as the integral of tangent squared of x times the tangent of x dx. And I will use this tangent squared piece in much the same way that we did way back when we were dealing with sines and cosines. I'm going to use the Pythagorean identity on this to rewrite it in terms of secant. And so again, just to remind ourselves, what does that identity look like? It looks like this. Tangent squared of x plus 1 equals secant squared. So if I just wanted tangent squared, I would have to subtract 1 from both sides. So tangent squared is secant squared minus 1. So I'm going to rewrite this as secant squared of x minus 1 times tangent of x integrated with respect to x. Okay, so now I've got both tangent and secant. I'm going to distribute through, and it's going to give me 2 integrals. The first one is going to be secant squared of x tangent of x dx, and the other one is just minus the integral of tangent of x dx. So I've basically distributed the tangent through and split it up into 2 separate integrals. So the first one is going to be the secant squared times tangent, that's right here. The other one will be minus just the tangent by itself, minus just the tangent by itself. This one, we can basically either look up so you can look this up. The approach to do this, I may have done an example. I know I did this in an example in Calc 1, but you could also look this up in an integral table. It involves the natural log of of secant in this case, if I remember correctly. So we'll look at that in a minute. But for this one, now we're going to do our U substitution. We've got to pick out, again, going back up to pieces that we're trying to work with. I need to pick out one of these two things to pull out of the whole thing. I could pull out the secant squared and know that tangent is the function that is the original function. The secant squared would be the derivative. Or I could pull out a secant tangent and know that secant was the original. And it turns out this will work either way. Come on, zoom back in. Okay, so I want to, for the first part of this, I want to let u be equal to one of these two pieces. I could let u be equal to secant of x, and that would mean that du, what's the derivative of secant? It's secant x tangent x dx. That would work. Or I could let u be equal to tangent of x, and what's the derivative of tangent of x? Secant squared of x dx. And notice that both of these combinations of a u times du give me a secant squared times a tangent. Same thing here. U times du would give me a secant squared times a tangent. Either one of these substitutions works for this one. We have a secant squared times a tangent. You can do either one of these two substitutions. Both will work. So there are some cases where this is what I was mentioning earlier. Sometimes you'll really have to pick one, but in this case, we can pick either, and it would give us exactly what we need. So I'm just gonna, I don't know, arbitrarily pick we'll just do I don't know, let's just arbitrarily do the top one, I guess. Okay, so that means that this first part is going to be rewritten exactly as we've got here. It's going to be the integral of secant of x times secant of x tangent of x dx. Here's my du, here is u. That's based on the top one that we picked. We could have split it up. Otherwise, this could have been my this and this could have been my du, and this could have been u if we'd used the other one that we crossed out. And this one, I'll just do it. This is the natural log of the absolute value of secant of x. And we will have a plus c on all of this when it's all said and done. This one, if you're interested, you can just look it up. I think I did this in one of those review videos that I posted from Calculus 1. You can go through those as well if you want to see this. And if people are interested, maybe I can, at the very end of this video, do one of these real quickly. So in the interest of time, though, I'm going to skip it for now. And at the end of the video, you feel like hanging on and watching, you can watch me go through this one. Okay. What am I doing? Oh, yeah, back to this. Integral of u du. So we've got the integral of u du minus the natural log of the absolute value of secant of x plus c. This piece will integrate to 1/2 u squared. And the u that we're using is secant of x. So this will be equivalent to 1/2 secant squared of x minus the natural log of the absolute value of secant of x plus c. And there is our answer. If you had taken this other approach, you would get an answer that looks different, right? It would wind up involving tangent here, but it would turn out to be equivalent. You could graph the two of them, and they would wind up looking exactly the same. You would see that, or you could even use trig identities to show that one is in fact equivalent to the other. So for now, I'll just leave it like that. Okay, so there's the answer to that. I want to do one more example. And then again, at the very end, I can come back and readdress this little point for a moment. Okay, so for our last example, I want to do the same thing. We just integrated tangent cubed. I want to now integrate secant cubed of x dx. How do we integrate secant cubed? This one is a tricky one. This one is really, really tricky. And you can try to do kind of what we did earlier, where you would rewrite this as secant squared times secant, and then replace the secant squared with something involving tangent squared. But it would not give you the right pieces to do what we've been doing in all of these problems. So this is sort of a special case. It's one that I just want to show you so you've seen it, but it's not one that I would necessarily expect you to know off the top of your head. This is, again, by far the trickiest one. Integrating secant cubed, even though it looks like it should be the same level of difficulty as the others, this is much trickier, and it's a different approach. And it's not something I will test you on. I'm not going to put this problem on an exam. Turns out in this case, the correct approach is to actually integrate by parts. It looks like we should be using the U substitution approach we've been using with all these other ones, but I mentioned earlier, sometimes we'll have to integrate by parts. This is one of those special cases where we've got to integrate by parts. And the way that we're going to do it is the following. So basically, we're going to let U be equal to secant of x, and dv is going to be the secant squared of x dx. I need this one to be the dv because this is something I know the integral of. I know that the integral of secant squared is tangent. So I had to pick a part of it that I'll actually be able to integrate. Du, when I take the derivative of secant, we will get secant of x tangent of x dx. And when we integrate dv, that's where we get tangent of x by itself. And so what we get is my integral of u dv, secant cubed dx, is going to be, so remember our integration by parts, this thing will be the same as u times v minus the integral of v du. So u times v, secant of x, tangent of x, minus the integral of v du, which is going to be, we'll just write it out, tangent of x times this other tangent of x winds up being, we get a tangent squared of x, times the secant of x that we pick up from right here, times dx. Okay, so here's what our integration by parts looks like so far. We've got part of the answer right here, and now we have another trigonometric integration problem that we have to deal with. How are we going to deal with this one? We have, again, sort of a tricky approach that we're going to do. I'm going to, again, recognize that I can't split this up and do a U substitution on this because I can't do the terms that we need that are getting way up there now. Maybe you can't even see these. Let me just stay down here. The terms that we need aren't here. If I tried to say, let's let u be the secant of x, and what would du be? Well, du, what's the derivative of secant? It's secant tangent. And that's fine if we have a secant squared tangent, but we don't have secant squared tangent, we have tangent squared secant. So this won't work. And if I tried to instead say, let's let u be equal to tangent of x, well, the derivative of tangent is secant squared, so same thing. It would work great if I had tangent times secant squared, but I don't have tangent times secant squared. I have tangent squared times secant. So this will not work either. Neither of the two plausible U substitutions we could try to do will work. This is not a U substitution problem. So what we're going to do instead is I'm going to rewrite this whole thing back in terms of secant. So earlier we were always trying to get a function and its derivative. We've just seen that that's not possible in this case. Even though we've got both tangents and secants, we don't have the right combination to set up a function and its derivative. So instead, I'm going to rewrite the whole thing back in terms of secant. So I'm going to rewrite this as, again, rewriting tangent squared. Tangent squared is secant squared minus 1 times secant of x dx. And that will give us the following. Secant x, tangent x, I'm just copying this part. I'm going to distribute through, and we will get the integral of secant cubed of x dx. That's this part times this part with a negative sign. For the second part, the negative sign will distribute through and cancel, and I will just have negative times a negative becomes positive, and it's just 1 times secant of x. So plus the integral of secant of x dx. This piece matches what we started with, and we're going to do a trick similar to when we would do integration by parts multiple times. I'm basically going to move that part kind of over to the other side, recognize that it shows up in more than one place, and basically go from there. The other one, this part, is another integral that we can look up in a table, and maybe down the line we can go through it, but it turns out this integral also involves the natural log. This is the natural log of secant of x plus tangent of x, if I remember correctly. And this piece gets moved, this piece gets moved back over to the other side. So we get, if I add this to both sides, so remember the whole thing was equal to this. This is what we started with. If I add that to both sides, I'll have 2 times the integral of secant cubed of x dx is equal to, what I'm left with is secant of x, tangent of x, plus this natural log of the absolute value of secant x plus tangent of x plus a c. And we set out to solve this integral, but we don't want the 2 there, so let's undo the 2 by dividing the whole thing by 2. And that is what our answer is. Our answer is the integral of secant cubed of x dx is secant of x tangent of x plus the natural log of the absolute value of secant of x plus tangent of x, whole thing over 2, plus some constant. And technically, when we divided everything by 2, this constant is different than this constant, so I'll just put a subscript here, a new constant, some other constant of integration, doesn't matter. So the hardest part in this, in these couple of problems, has just been basically knowing this integral right here, what's the integral of secant, and then up here, what was the integral of tangent. And maybe I can address these here. So if you don't care about those and just want to look them up in a table, honestly, the integral of tangent is probably worth remembering. This one, slightly less so, but let's see if we can kind of go through these here. So if you want to be done, you can be done. If you want to stick around, let's go through those. So how do we get these 2 integrals that we wound up just using, the ones that I said you can just look up in an integral table? So let's start with the integral of tangent of x dx. We can get this by rewriting in terms of sines and cosines and going from there. So this can be rewritten. If I rewrite tangent, I can rewrite it as the integral of sine of x over cosine of x. dx. And now we've got a situation where we can do a U substitution. I see two functions, each of which is the derivative of the other, mod some sine in this case. I want to pick the one that doesn't introduce unnecessary negative signs. So I'm going to let, in this case, I'm going to basically let, let's see here. I want to let u be equal to cosine of x, and that means that du will be equal to the sine of x dx with a negative sign. Okay, so that's one way that we could pick this. Good. So far, so good. Okay. Once I've picked this, what we wind up being able to do is rewrite this. So again, here's my u, here's its derivative. The derivative of cosine is negative sine. And what I've got is, if I put in a negative sign here and a negative sign here, I now have the negative integral of that piece, which is my du, over that piece, which is my u. And so we just have the negative integral of du over u, or negative integral of 1 over u du, if that's easier for you to spot. This is something that integrates natural log, right? 1 over x, the integral of 1 over x is natural log of the absolute value of x. This is one we learned back in Calc 1. So this is going to be the negative natural log of the absolute value of u. So far, so good. So we have this thing now written in terms of u, and let me just add in my plus c before I forget that. I have it written in terms of u, but we want it written back in terms of the original variable x. So I can plug x back into this, and we will get negative the natural log of the absolute value of cosine of x plus c. This looks a little bit different than what I wrote up here, right? Here we said it was the natural log of secant of x, but notice the sign is different in this case. I said the integral of tangent is natural log of secant of x, right? The sign stayed the same from here to here, whereas down here, the sign has flipped. How do we deal with this sign flip? Well, we need to remember our log rules and recognize that I could rewrite this whole thing as the natural log of the absolute value of cosine of x to that negative 1 power plus c. And what does it mean to take something to the negative 1 power? That's just doing 1 over it. So this is the natural log of 1 over the absolute value of cosine of x. But what is 1 over the absolute value of cosine? So what's 1 over cosine? That is secant. And the absolute value carries through because if this always has to be positive, then so does this. So we need those absolute values to carry through. And that's where we get the integral of tangent now written efficiently and without a sign flip. So this one does not involve the sign flip. You could also use this expression. This expression and this expression are algebraically equivalent. So just keep that in mind. How do we do the integral for the other one? And so for the other one, for the integral of secant of x dx, this one is also a super tricky one. Surprisingly tricky. The way that you do this, and it's not something, again, I don't expect you to have some intuition for this magically, but the idea is I'm going to take secant of x, and I'm going to actually multiply it by 1 in a very special form. I'm going to multiply it by 1, written as secant of x plus tangent of x over secant of x plus tangent of x dx. Where would we know to do this from? It basically is some intuition that's only built kind of after the fact. You wouldn't, in a million years, this is one of those things where the person that figured this out had probably been studying this problem for an incredibly long time, and finally something like this clicked with them, and they spent like 6 months working on it, and then it finally figured out a way to get this all to work. So don't feel bad if you don't have the intuition for this. I certainly don't have the intuition for this, but that is the trick. So we'll multiply through, and what we wind up getting is, in this case, we get the integral of, we get secant squared of x on top plus secant x tangent x, and on the bottom we still have secant x plus tangent x, whole thing times dx. And from here, there's yet another trick. We're going to be able to do a U substitution. And what you should recognize is these two pieces in the numerator look exactly like the two pieces we were looking for that were supposed to be du's previously. Right? So the derivative of tangent, for example, is this secant squared of x. And the derivative of secant is secant tangent. And it turns out that's exactly what I have in the bottom. I have both a secant and a tangent. So our substitution, our U substitution, is we're going to let U just be equal to the denominator. It's going to be equal to secant of x plus tangent of x. That means that du will be the derivatives of these. So what's the derivative of secant? It's secant x tangent x. And what's the derivative of the tangent? Well, that is secant squared of x, whole thing times dx. And now what I have exactly is du on top, this whole thing, over u. And we've got the integral of du over u. And from there, that is the natural log of absolute value of u, is what that integrates to. Again, same thing, natural log plus c. And all we need to do is plug in our result and write this back in terms of x. U is equal to secant of x plus tangent of x. And there is this second result. But it requires basically two very tricky parts. One is multiplying by this part that you would never have intuition for, and the second one is recognizing that what's on top here is in fact already the derivative of what's on the bottom here. And that allows us to do this particular U substitution. So that's where these two come from. Again, not something I'm going to put on an exam. Secant turns out to be a tricky thing to deal with. So focus on all of these problems that we were doing up here. There's a gajillion of them. And you'll get plenty of practice with these, again, on the homework. But don't worry about reproducing results like this one or the two that we did down below on an exam. I will not make you do anything like those on an exam.